Today we are going to discuss about Unit 2 switched reluctance motor. In this unit we are going to discuss about the following main topics: the power semiconductor switching circuits for SRM or the power controllers, torque production of SRM, closed loop control analysis of SRM, sensorless operation of SRM. Now let us look into the first topic, power semiconductor switching circuits for SRM, which is otherwise called as power controllers. The selection of the controller mainly depends upon the application. The main aspects of a SRM drives are the converter design. The main objective in the converter design are performance and the cost of the drive. So the power semiconductor switching circuits are normally classified as 5 types. The first one is 2 power semiconductor switching devices per phase and 2 diodes. Second type is N+1 power semiconductor switching devices and N+1 diodes. Third type is phase winding using bifilar wires. Fourth type is split link circuit used with even phase number. And the fifth type is C-dump circuit. Let us look into each type one by one. So the first type is 2 power semiconductor switching devices per phase and 2 diodes. Here we have used 6 semiconductor switching devices and 6 diodes. Now we are providing DC supply to this circuit. In order to energize the phase winding A, we have to switch on the 2 semiconductor switching devices like T1 and T2. So only it is named as 2 power semiconductor switching devices. So if T1 and T2 are turned on and if you are providing DC supply to this circuit, the winding A will be energized. After receiving signal from the rotor position sensor, if T1 and T2 are turned off, the current flowing in the phase winding A is supplied through the diodes D1 and D2 back to the supply itself. Likewise, the phase winding B and C will also operate. Let us detailedly discuss this operation in the next slides. So, phase winding A is connected to the DC supply through the power semiconductor devices T1 and T2. Depending upon the rotor position, when the phase winding A is to be energized, the devices T1 and T2 are turned on. When the phase winding is to be disconnected from the supply, this instant is dependent on the position of the shaft. The devices T1 and T2 are turned off. The stored energy in the phase winding A tends to maintain the current in the same direction. This current passes from the phase winding through the diodes D1 and D2 to the supply. Thus, the stored energy is fed back to the mains. Similarly, the phase winding B and C are also switched on to the supply and switched off from the supply in a cyclic manner. This circuit requires 2 power semiconductor devices and 2 diodes for each phase winding. For high-speed operation, it is required to see that the stored energy can be fed back to the mains within the available period. Usually, the upper devices T1, T3 and T5 are turned on and off from the signals obtained from the rotor position sensor. The duration of conduction or the angle of conduction theta can be controlled by using suitable control circuitry. The lower devices T2, T4 and T6 are controlled from the signals obtained by chopping frequency signals. The current in the phase winding is the result of logical unding of the rotor position sensor and the chopping frequency. That is, the current flowing in the phase winding is due to the signals received from the rotor position sensor and also the chopping frequency signal. So only we are mentioning it as logical unding. By the presence of both the signals, there is a flow of current. As a result, it is possible to vary the effective phase current from a very low value to very high value. For varying this, the following methods are normally adopted. The first method is by varying the duty cycle of the chopper or the semiconductor switching devices. And the second method is by varying the conduction angle of the devices. And this depends upon the angle at which the firing pulses are sent to the devices for triggering on. Next, let us discuss about the merits and demerits of this type. So the merits are control of each phase is completely independent of other phases. the converter is able to freewheel during the chopping period at low speeds, which helps to reduce the switching frequency and thus the switching losses of the converter. The third one is the energy from the outgoing phase is fed back to the source, which results in utilization of energy. So these 3 points are the merits of this type, and the demerits are nothing but higher number of switching devices are used in each phase, which makes the converter expensive and also used for low voltage applications. Now let us look into the second type. In this type we are going to use N+1 power semiconductor switching devices and N+1 diodes. Now this is the circuit diagram of N+1 power semiconductor switching devices and N+1 diodes. This circuit uses less number of power switching circuits and diodes as shown in the figure. And compared to the previous diagram, previous type, we have 6 semiconductor switching devices and 6 diodes, but here we have only 4 thyristor devices. Those devices are the semiconductor switching devices, and we have only 4 diodes here. So the number of switches and the number of diodes are reduced in this circuit. When the SR switching devices T and T1 are turned on, the phase winding A will be energized from the DC supply. When these devices are turned off, the stored energy in the phase winding is fed back to the mains through the diodes D1 and D. When the devices T and T2 are turned on, the phase winding B is energized, and when they are turned off, the stored energy is B is fed back to the supply through the diodes D1 and D. Likewise, the phase winding C is also switched on and off from the mains. The cycle repeats like this. This circuit makes use of N+1 power semiconductor switching devices and N+1 diodes, where N is equal to the number of phases. Now let us detailedly look into the merits and demerits of this type. The converter uses low number of switching devices, which reduces the cost of the converter. And the second merit is the converter is able to freewheel during the chopping, thus reducing the switching frequency and losses. And the third one is the voltage rating of all the switching devices and the diodes are VDC, which is relatively low. That is the voltage rating of the devices and diodes are only VDC only. It is a very low voltage. The fourth one is the energy for the outgoing phases transferred back into the source, which results in useful utilization of energy and also improves the efficiency. The demerits are, the first one is disability to magnetize a phase while the outgoing phase is still demagnetizing, which results in higher torque ripple during commutation. That is, when the switches are turned off, it will not immediately demagnetize the current flowing through the phase winding. So because of this, a higher torque ripple is produced during the commutation time. Second point, at high speeds of outgoing phase cannot be de-energized fast enough because the common switch T keeps turning on intermediately, disabling the forced demagnetization. Here we have a common thyristor T. Even though if we turn off T1, T2, T3, etc., the demagnetization does not takes place suddenly because the thyristor T is always in operation. The third point, the common switch conducts for all the phases and thus have higher switching stress. Now, in order to avoid the drawbacks in the previous type, we are going for the third type. The third type is nothing but phase winding using bifilar wires. Now, these windings are marked in the bifilar type. That is, the A winding is split as A and A dash. Similarly, B is split as B and B dash. Both are magnetically coupled. Similarly, C is also split as C and C dash. Both are magnetically coupled. And we have a dot representation for current entry. Each phase winding has two exactly similar phase windings as shown in the figure. For this, bifilar wires are used. Each phase consists of two identical windings and are magnetically coupled when one of them are excited. The purpose of bifilar winding is for bipolar excitation with reduced number of switching elements. In this case, the switches used are only 3 and the diodes are also only 3. So the number of diodes and the switching devices are reduced compared to the previous 2 types. When T1 is turned on, the DC current passes through the phase winding A. When T1 is turned off, the stored energy in the magnetic field is fed back to the DC source through the winding A' and D1. Similarly, the other two devices also will operate in a sequential way depending upon the signals received from the rotor position sensor and the chopping signals for the PWM technique obtained from the controller. Now let us look into the merits of this type. The merits are: the converter uses low number of switching devices, thus reducing the cost of the converter. And second one, the converter allows fast demagnetization of phases during commutation. And the demerits are discussed below. The first one is bipolar winding suffers from double number of connections. And second point, a poor utilization of copper. And third one, freewheeling is not possible during chopping as the phases have minus VDC. So this causes higher ripples in the current and torque during chopping. And the fourth point is the imperfection in the coupling between the two winding causes voltage spikes during turn-off. And the last point is the copper loss associated with the auxiliary winding is unacceptably a higher value, so it cannot be used for many of the applications. Now, in order to overcome all the drawbacks in the third type, we are going for the fourth type, which is nothing but the split link circuit used with even phase number. And this is a circuit diagram of this, and here also we are using 6 semiconductor switches and 6 diodes, and the phase winding is split into A and A', B and B', and C and C'. DC supply is provided to the entire circuit, and here we are having 2 storage capacitors C1 and C2, which is not present in the previous 3 types. The circuit shown in the figure is used in a range of highly efficient drives from 4 to 80 kilowatts. The main power supply is split into 2 halves using the split capacitors C1 and C2. During conduction, energy is supplied to the phases by one half of the power supply. So during commutation period, the phases demagnetize into other half of the power supply. So when the switch T1 is turned on, the phase winding 1 is energized by the capacitor C1. When the switch T1 is turned off, the stored energy in the phase winding 1 is fed back to the capacitor C2 through the diode D4. When T4 is turned on by the capacitor C2, the phase winding 4 is energized. When T4 is turned off, the stored energy in the winding is fed back through the diode D1 to the storage capacitor C1. The similar operation takes place in the remaining winding also. Here the thyristors are marked as T1, T3, T5 and T4, T6 and T2. Similarly, the diodes are also marked here. Now let us look into the merits of this. It requires lower number of switching devices, and there is faster demagnetization of phases during commutation, because during the turn on of the switching circuit, switching devices, we will be providing only one half of the supply. So during the remaining half of the supply, the demagnetization occurs. So the demerits of this type are: during chopping, freewheeling is not possible as the phasor have the voltage VDC divided by 2. So this causes higher switching frequency and more losses. Second one is, this is not possible for low voltage application. So only for high voltage applications we can split the voltage into 2 halves and we can use this type. For low voltage applications it is not at all possible. And third point is, the converter is fewer fault tolerant, as fault in any phase will unbalance the other phase that is connected to it. And let us come to the fifth type, which is nothing but the C-dump circuit. Now this is a circuit diagram of C-dump circuit. So this circuit diagram consists of 3 switching devices and 3 diodes. In addition to this 3 switching devices, we have an additional switching device commonly used, which is the thyristor T, and an additional diode commonly used, which is D. So we have n+1 switching devices and n+1 diodes, and here we have used the inductance as the storage element, and this capacitor is used for fast demagnetization. So in the CDUM circuit shown in the figure, the device count is reduced to n+1 additional devices to bleed the stored energy from the dump capacitor C back to the supply via the step-down chopper circuit. The main capacitor voltage is maintained well above the supply to permit rapid defluxing after commutation. A control failure in the energy recovery circuit would result in the rapid buildup of charge on the capacitor, and if protective measures were not taken, the entire converter would fail from over voltage. And let us discuss about the demerits of this type. The dump capacitor voltage is maintained as -2 VDC. This capacitor voltage is -2 VDC, which is for fast demagnetization. But the use of a capacitor and an inductor in the dump circuit, and also the voltage rating of the devices, is twice the bus voltage. So only there is a possibility of occurrence of over voltage, and which may sometimes lead to the failure of the devices also. And second point is monitoring of the dump capacitor voltage across C and control of the dump switch T makes the converter very complicated, and also the converter does not allow freewheeling. Now in the previous topic we have discussed about the power controllers, and we have discussed about the merits and demerits of all the types also. And let us look into the second topic, which is nothing but the torque production in the switched reluctance motor. The torque is produced due to the variable reluctance principle. So the flux linkage lambda due to the excitation of the winding can be calculated using the formula lambda is equal to L into I, and we are considering this as equation number 1. According to the Faraday's law of electromagnetic induction, the EMF E is produced due to the rate of change of flux. So we will be getting E is equal to minus d pi by dt, and this is assumed as equation number 2. Now from the first equation we can substitute the expression for lambda in the second equation. So substituting lambda from equation number 1 in equation number 2. So E is equal to minus of instead of d lambda by dt, now we are considering the partial differentiation dou lambda by dou t, and instead of lambda we have used L into I here. So we have to differentiate this L into I with respect to the time period t in a partial differentiation manner. So this is nothing but we have to apply the UV method. So minus L into dou I divided by dou t minus I into dou L by dou t. Now in the second term we are going to multiply by dou theta divided by dou t. So multiply and divide by dou theta in the second term. So E is nothing but minus L into dou I by dou t minus I into dou L by dou theta, and the second term is multiplied by dou theta divided by dou t. Now here in the numerator we are multiplying by dou theta, and in the denominator we are dividing by dou theta. So the equation does not get affected. So which is equal to minus L into dou I by dou t minus I into dou L by dou theta is written as it is, and dou theta by dou t is nothing but omega, because we know that theta is equal to omega into t. So omega is nothing but dou theta by dou t. So E is nothing but minus of the whole bracket L into dou I by dou t plus I into dou L by dou theta into omega, close the bracket. Now this is assumed as equation number 3. Now if you are considering only the magnitude alone, so the EMF becomes L into dou I by dou t plus I into dou L by dou theta into omega, and this is assumed as equation number 4. Next we calculate the energy stored in the magnetic field. Energy is represented by W suffix E, which is equivalent to half Li square, and this is represented as equation number 5. So the mechanical power developed is equivalent to the power input to the motor minus power due to variation in the stored energy. Now let us calculate the power input to the motor first. The power input is nothing but product of voltage and the current, so it is equivalent to E into I, which is nothing but equation number 6. Now already we have derived an expression for E, so we are replacing that by the expression. So L into dou I by dou t plus I into omega into dou L by dou theta, the whole multiplied by I. Next we multiply I with each of the term. So we will be getting Li dou I by dou t plus I square omega dou L by dou theta, and this is assumed as equation number 7. Next we calculate the power due to the variation in the stored energy. Since we are calculating the variation in the stored energy, we are using d by dt of We. So d by dt of half Li square. Next we have to differentiate this expression. So we are taking the constant 1 by 2 outside, and if we are differentiating Li square by uv method, first we are keeping L as it is and we are differentiating I. So we will be getting 2I dou I by dou t plus, then we are keeping I square as it is and we are differentiating L. So I square into dou L by dou t. Next we are splitting each and every term. So 1 by 2 into 2 Li dou I by dou t plus half into I square dou L by dou t. Next this 2 and 2 will be getting cancelled. So we will be getting Li dou I by dou t plus I square divided by 2 dou L by dou t. And here also we don't have the angular velocity expression. So we are multiplying the second term by dou theta and dividing by dou theta. So the next step is Li into dou I by dou t plus I square by 2 dou L by dou theta into dou theta divided by dou t. So which is written as Li dou I by dou t plus I square by 2 dou L by dou theta, and this dou theta by dou t is written as omega. So this is assumed as equation number 8. Now in order to calculate the mechanical power, we have to subtract the mechanical power input and the power due to variation in the stored energy. So subtracting 8 from equation number 7. So if we are subtracting, we will be getting the mechanical power developed as Pm. Pm is equivalent to Li dou I by dou t plus I square omega into dou L by dou theta. This is the power input minus Li dou I by dou t minus I square by 2 omega into dou L by dou theta. This is the power due to variation in the stored energy. And if we subtract this, the two common terms Li dou I by dou t will be getting cancelled, and if you subtract these two terms, we will be getting half into I square omega dou L by dou theta, and this is assumed as equation number 9. In general, the mechanical power developed can be calculated using the formula 2 pi nt divided by 60. So this can be separated as 2 pi n by 60 separately and multiplied by t, and this 2 pi n by 60 is nothing but omega into t. So the mechanical power is nothing but omega into t. This is assumed as equation number 10, where omega is the angular velocity and t is the electromagnetic torque developed. And from the 10th equation, we can calculate the electromagnetic torque developed as Pm divided by omega, which is assumed as equation number 11. Now, substituting the expression for Pm from the 9th equation, we can calculate the torque value. So, substituting 9 in 11, we will be getting T is equivalent to half I square omega dou L by dou theta, the whole divided by omega. So the omega and omega will be getting cancelled. So the final expression for electromagnetic torque T is equal to 1 by 2 into I square dou L by dou theta, and this is assumed as equation number 12. This is the final expression for the torque produced in the switched reluctance motor. Next, let us look into the third topic of today's presentation, that is the closed loop control analysis of SRM. Now this is the circuit diagram of closed loop control analysis of SRM. So the SRM for the variable speed applications is a robust, reliable and almost maintenance-free electrical drive which is suitable for industrial, transport and domestic sector. The SRM is always operated with the closed loop control. This figure shows the general closed loop block diagram of SRM. The block diagram consists of power converter, SRM, controller, current sensors and encoder. Here the encoder senses the encoder. The encoder senses the rotor position and sends it to the control block. The current sensor also senses the motor current and sends it to the controller. Here we can set the reference signal by using a potentiometer. This signal is also fed to the controller block. So this controller block processes all the signals and generates the control PWM signals. So these signals are fed to the power semiconductor switching circuit. So depending upon the energization of phase winding, the SRM rotates according to the desired speed. In the controller block, we can incorporate different control techniques like voltage SRM control with the speed closed loop. And the second one, the motor starts from any position with the rotor alignment, and two directions of rotation, that is the clockwise and the anti-clockwise rotations of direction are the clockwise and the counterclockwise direction. And the fourth one is motoring mode. And fifth one is minimum speed, which is set by the user, and the maximum speed, this can also be set by the user. And finally, the encoder position reference for commutation. So by incorporating these different techniques, we can send the signals from the controller block, and based on this we can maintain the closed loop control of SRM. Next, we will discuss about the final topic of today's presentation, sensorless operation of SRM. Now look at the circuit diagram of sensorless operation. So in this block diagram, we will be having the PID controller, reference current generator, hysteresis current generator, inverter module, SRM motor, flux estimator, fuzzy angle estimator, filter, and we have a differentiation block also. And here we have the speed comparator for producing the speed error signals by comparing with the reference also. We will detailedly discuss about the operation in the next slides. So the fundamental principle of operation of a SRM is based on the variation in the flux linkage with the change in the angular position of the rotor. The sensorless scheme relies on the fuzzy based rotor position estimator model of the SRM drive. So the fuzzy based is nothing but the values are normally varying from 0 to 1. It will take only the intermediate values and it does not take the 0 or 1. The dynamics of the SRM drive can be represented by a set of non-linear first order differential equations. So only we are including the differential block in the block diagram. So the block diagram consists of the sensorless scheme shown in the figure. It consists of various subsystems necessary for PID speed controlled SRM drive with fuzzy logic used as a rotor position estimator. The flux estimator produces the flux linkage by using the phase voltage and current as the inputs. The experimental data of flux linkage and the phase current are used as inputs to the fuzzy estimator and map them in the fuzzy rule base for estimating the angle as the output. That is, we are going to follow the if-then rules. So if the value of phase current and if the value of flux linkage is like this, what is the value of angle? So likewise we are setting the rule base, and based on this we can find out the output angle. The suitable type of low pass filter has been used to produce a refined estimated angle for inverter operation and simultaneously used to obtain the estimated speed for comparison. Now we are giving the reference speed as input to this speed comparator unit, and the motor speed is measured and it is given as another input, which is nothing but omega m. So the speed error signal is given to the PID controller, and this function of this proportional integral derivative controller is to reduce the speed error and reduce the rate of change of error also. And this signal is given to the reference current generator, and the difference between the reference and the actual speed, if they varies, and the sign value is also given to the reference current generator, and based on this it produces a hysteresis current or I reference current to the hysteresis current controller, and based on the signals, the hysteresis current controller receives the reference current value from the reference current generator, and it also receives the three-phase currents from the SRM drive, which is nothing but IABC, and this currents IABC and this reference currents are given as input to the hysteresis current controller, and based on this it produces the output signals, and these signals are used to trigger the power semiconductor devices in the inverter module. And for this inverter module we are also providing a power supply of DC supply. The output of the inverter is nothing but AC. So from the AC output we are calculating the individual phase voltages as VA, VB and VC, and similarly the individual phase currents IA, IB and IC can also be obtained here, and these phase currents are given as input to the hysteresis current controller, and they are also given as input to the fuzzy angle estimator also, and based on this individual phase currents we are calculating the I0 value, and based on the individual phase voltages we are calculating the V0 value, and this I0 and V0 are given as inputs to the flux estimator, and based on this it produces a output flux phi, and this flux value and the individual phase currents IA and IA, IB, IC are given as inputs to the fuzzy angle estimator, and based on these two inputs it estimates the output angle theta, and during the conversion of this phase currents and flux into the angle there will be some ripple content present, and in order to reduce the ripple content we are using a filter here, and this estimated angle is only theta, but the speed is nothing but the omega m, so it is nothing but d theta divided by dt. So we have to find out the variation of this angle, so we are finding out d by dt of theta, and this is nothing but our omega m. So this is the actual motor speed, and this speed is given as input to the speed comparator, which also receives a reference speed, and then it produces the speed error, and based on this the circuit operates. And that's all about the sensor plus operation of